Hi, everyone. Great to be here at NANOG 85. Unfortunately, virtually, but still with you. My name is Jeff Tansura. I'm with Microsoft, Senior Principal Network Architect at Azure Networking, working on next-gen data centers, networking, machine learning clusters, and such. I would like to shed some light on how we operate our data center networks. We are performing thousands of changes every day. Pretty much every minute there is a change. So I would like to kind of show you or guide you through how we manage to build most reliable network. So reliability is a struggle for everyone. At particular size, at particular scale, stuff starts breaking. No one is safe from it. But it's our job as network architect, as data center architect, to make sure that our changes can go ahead, that they don't affect each other, and that our customers, most importantly, are not affected by them. So the agenda for today's talk is really to show you how large Azure really is, so you understand the problem with the scale, and guide you through the change procedure. How do we do changes at scale and without really any negative impact? Obviously, there's always problem and unexpected consequences, but normally we perform thousands of changes a day without any negative impact. And we will go through different stages and how we achieve the state. So number one is obviously you need to abstract and contain the change. So change in one place doesn't affect another one. I'll show you how we simulate, emulate, and at the end, obviously, validate what we've done. So Azure is one of the biggest networks in the world. Before we go further, I would like really to focus, what does it mean to be hyperscale? Its ability of architecture to scale with increasing demand and do so over common infrastructure. And we achieve this by really adhering to hyperscale design principle. We have fully disaggregated hardware from software in our networking. So we choose best hardware where it should be, and then we decide which software to run on it. As you know, Microsoft started Sonic Effort, which is today one of the best available choices in open source world. We also use vendor software, and all of this could be done interchangeable on top of hardware we decide to use. Number two principle, all complexity is moved to the edge. All complex encapsulation, firewalling, enforcements are done at the host. Network is kept simple to provide reachability. And this allows to scale to pretty much any size. Number three, and we'll focus to some degree on that, we strictly follow pod principle. So when there's a new change, it's always within the pod. There's versioning between pods. This allows to build a network of pretty much any size because the complexity is always contained within the pod. Just to give you some impression, this is how large we are. 61 regions, thousands of miles of fiber, many peerings. And it keeps growing, and it grows like crazy every day, every month, every year. To give some impression, this is how single building within data center block looks like. This is how a block looks like. This is how data center with all the auxiliary things looks like, and so forth. What you see here is not the biggest one. The biggest one, 1 gigawatt plus, are yet to come. So the infrastructure is growing at huge tempo, and without automation, without ability to abstract and perform changes every second of the day, you wouldn't be able to do so. And changes cause outages. It's well known, this information from Facebook, but it's somewhat similar everywhere where there's a lot of state, a lot of changes, and large infrastructure. So how do we build and operate the most reliable? You might argue with my statement, but we are very reliable. Number one, and probably the most important point here, is to build right foundation. So ability to abstract and self-contain different building blocks. How do we build data center? And we are not really unique here. It's how any large data center pretty much looks like. It's what you do with the state and data. Rack is a unit that has reachability to all the compute or storage or any other device that needs to be accessed throughout the network and reachable. There's full reachability within the rack. Rack makes a pod. Again, there's full reachability between different racks in the pod. However, any change within the rack is invisible within the pod. Within data center, we follow exactly the same approach. Racks are fully reachable from data center perspective. However, all the changes within the racks are absolutely invisible within the data center. They're completely abstracted. And from routing perspective, aggregated, if you wish. Same goes when we start going out of data center. Again, all the data that is within data center is aggregated. All the changes are completely hidden, and all the changes are self-contained. And finally, this is how region looks like that connects to Microsoft One that provides reachability across the world. The basic foundation layer here is self-contained. As you could see, self-contained boundaries are rack. So there's single v4, single v6 subnet, and all the changes within subnet are not propagated up. Within the rack, same story. There is subnet that attached or assigned to a pod that doesn't change any changes. Same goes for data center. This allows us to perform different changes within racks within same pod. This allows us to perform changes within pods within data center and in data centers. Practically, one change should never interact in any way with other changes. Let's touch upon routing. Within routing that adheres to the same principle, it is impossible to provide self-containment. What are the requirements for routing at large scale? Obviously, it's to reduce number of routes to the strictly necessary minimum. TCOM is finite. We would like to be able to grow number of devices within data center without replacing switches every 6 months. So we are trying to keep number of routes as small as possible. On another side, we would like to keep enough details to prevent black holing, because when we remove too many details, it inevitably leads to, in best case, very, very ineffective routing, in worst case, to black holing. Two more very important steps here is that as any large data center, we're multi-planar. The plans are massively distributed to provide reachability that is contained within the plane, right? So while there is kind of rule of thumb to use value-free routing, because we care about amount of time it takes traffic to take from one point to another. When there's a failure, we implemented so-called bounds, and we'll go through it why we do it. So a naive approach is really summarize everything. It's now it's too little information. The problem, it is preventing us from understanding next step failure and can lead to black holing. And when plane gets disconnected, in order to get to through another plane, it has to go outside of data center, which brings latency and plane failure. And while not very significant for regular TCP traffic, really reduce performance of storage, anything that's related to ML and RDMA traffic. Another new approach is to deploy an IGP. We know there's a lot of work going on flood reduction, on making IGPs more suitable for data center. However, basically IGP floods extensively, which is a problem at large scale. Blast radius is a whole IGP domain. So we are not using IGP either. The pragmatic approach we've taken is path vector. It's well known we are big BGP user. However, rather than using value-free, we also want bounds. This allows us to have backup always available. And when plan is failing, our connectivity to the plane from outside is failing, there's always longer route through bounds available. And this is with minimum path hunting because, as I said, it's only allowed to bounce once. So this is how we provide self-contained complexity. This is how we provide ability to implement changes at any point, at any time, without affecting customers. How do we perform them without having any negative impact? We start with simulation. I'll guide you through the change verification system process. We create a manual operation procedure mob that is really intent definition of change to be performed. Using metadata, it derives topology and devices involved and all the information about devices, creates configuration, and also stages simulation and emulation. After simulation is done and routing tables post-change are retrieved, they're being validated by our Spock system, which I'll describe in more details. If result is positive, change will go into the system and be performed. If it's negative, it's rolled back. Actually, it hasn't been performed yet. It stopped and goes back to either manual validation or draw out some system validations that are performed here. So what is the difference between emulation and simulation? Emulation is one VM per router. Simulation is one VM for all the routers. So the scale is completely different. When we emulate, we can emulate subset of a data center. We can build network of thousands of switches and routers, however, not larger than that. Simulation could easily simulate entire Azure region or entire Azure if needed. Speed is very different too. The emulation is non-interactive. It's actually required to build, to fetch the images that are used in production, fetch the configurations that are used in production, and spin out VMs that will run it. While simulation is very, very lightweight, at same container level deployment that can build thousands of nodes in minutes. What's also important, and the difference here, from fidelity perspective, we make a big point that the virtual hardware that used in emulation is really provide exactly the same functionality as real hardware used on the devices. While in simulation, it's just an LS in production reads. So again, it doesn't require any forwarding plane involvement here. So simulation. Before you go and build very, very complex plane, you are trying to test it. We are doing exactly the same. So network logic solver is modeling behavior of routing protocol, so BGP in this case. If you look at changes at large scale, very often they require change in routing policies. And this is what's exactly modeled. So what we can do is to change the intent, run the BGP processes, get the routing table, and compare operational state of post-test routing tables to the intended ones. It's very efficient, it's very fast, and allows to at least figure out that our changes to the routing policies aren't in conflict with intent. Emulation. After MOP is being applied to the system, metadata provides us topology, devices, vendors, and all the information that's needed to build a twin. So emulation factually builds exactly the same network virtualized as in real data center. So exactly the same image is taken with regards to software, exactly the same configuration is taken as running on the device. The only difference is that we are running them in VM, so it's virtualized hardware versus real hardware in production. However, again, we make a point to work with our vendors to work on site to make sure that virtualized hardware exhibit exactly the same behavior as real hardware. And we run hundreds of millions of hours on Azure every year to validate. So typical usage scenario. After MOP is done and there is an intent-based definition of a change, we create an emulated replica. So it's fully automated. There's nothing needed to be done manually. Then change is applied to emulated replica. So the end result is exactly the same as we would apply, as if we would apply same change to the production network. The end result of replica is then run through our Z3 verifier, and the end result is pass or fail. If it's pass, we can proceed with the change. If it fails, it goes back. The validation is a very interesting point, right? You can simulate and emulate as much as you want. We all know that networks are not always predictable. There are inconsistencies between RIPs and FIPS, between what routing protocol sees versus forwarding sees. So ability to validate at scale and continuously is as important as ability to simulate and emulate. So what we do, we use what's known as formal method verification. And in order to do so, we pull forwarding table from all our devices in the network on a regular basis, and then they're compared to intended state. There is also configurational retrievals that compare configurational state to operational state, to FIPS, to state of routing protocols. So all of these changes are done on pretty much 5, 10, 15 minutes basis, depending where you are and when it's needed. So, and last is overview of SPOC, which is our system that actually does verification and validation. It's a testing framework we read internally in Microsoft. It uses assertions on invariants. So you could see here an example of code and the specification as a test. Anytime there's any change, there's always test code that's applied to it. If there is none, it's not allowed, actually. Change cannot be performed. So when there's a change, for example, we want to validate that every Tor router has a default route. It needs to be present in BGP RIP. It needs to be present in RIP. It needs to be present in FIP. So when we retrieve the FIP state, we have the intended state that runs through this code through every statement that should be present and validates if everything that's present in FIP is available on one side. On another side, that everything is available in FIP should actually be there. And this is done at scale of Azure. So after changes, this verification is mandatory. Between changes, it's run on continuous basis. This is how we ensure the changes we perform don't affect our customers. So to summarize, we abstract, simulate, emulate, and validate. And this allows us to grow at really, really high speed. We perform, as I said, thousands of changes a day, everywhere in the network. And it doesn't affect our reliability. It doesn't affect our agility. So we could go as fast as business requires us without affecting our customers. And we are hiring everywhere Microsoft. If you are interested, you see we are solving really, really interesting problems. You're more than welcome to join us. Thank you so much.